All right, welcome to The Explainer. Today, we're diving into one of the weirdest, but also one of the most important ideas in all of science. We're talking about the bizarre dual identity of, well, pretty much everything. It's a concept that really makes you question what reality even is. So let's start with a simple question. Is light a wave or is it a particle? I mean, for centuries, this was one of the biggest throwdowns in physics. You had scientists lined up on both sides, totally convinced they were right. But the answer? Well, it turned out to be way more mind-bending than anyone could have possibly guessed. So where does this all begin? Our story really kicks off with this nagging little mystery that the physics of the time, what we now call classical physics, just couldn't explain. It's a phenomenon called the photoelectric effect. Now, on the surface, it seems simple enough, right? You take a beam of light, you shine it on a metal plate, and that light's energy can actually knock electrons right off the metal. These little escaping electrons are called photoelectrons, and once they start moving, they create an electric current. Seems pretty straightforward. But the details? Oh, the details were total head-scratcher for scientists back then. Okay, before we go any further, we need to get one key concept down. Just imagine the electrons are kind of trapped inside that metal. To get out, they have to pay a sort of energy toll. You can think of it like an escape fee. In physics, we call this the work function. It's the absolute rock-bottom minimum amount of energy an electron needs to just break free from the surface. And here's where things start to get really weird. You would think, logically, that if you used a brighter, more intense light, you'd be hitting those electrons with more energy, right? They should fly out way faster. But nope, that's not what the experiments showed. Take a look at this graph. It doesn't matter if the light intensity is low, medium, or high, the energy of the fastest electrons stays exactly the same. What did matter was the light's color, its frequency, not its brightness. And that was the first huge clue that the old theories were in big trouble. And if that wasn't strange enough, the second clue was even more bizarre. Scientists figured out that every metal has its own specific cutoff frequency. We call it the threshold frequency. If the light you're using is below that frequency, absolutely nothing happens. No electrons pop out. You could blast that metal with the brightest red light in the universe for a year, and not a single electron would budge. But then you shine even the faintest little violet light on it, which has a higher frequency, and boom, electrons shoot out instantly. It's like trying to open a lock with the wrong key. It doesn't matter how hard you push. So, let's be super clear here. The old theory, the one that treated light like a big, continuous wave spreading out its energy, it was a total failure. It said any light should work if it's bright enough. It said brighter light should mean faster electrons. It couldn't explain why the electrons came out instantly. The theory was wrong on every single point. It was completely, totally broken. So you've got this massive problem that just stumped everybody. It needed a totally new idea, a complete revolution in thinking. And in 1905, along comes a young Albert Einstein, and he provides a solution that would change the course of physics forever. Einstein said, okay, let's stop thinking about light as a continuous wave. Let's picture it as a stream of tiny, individual packets of energy, like little energy bullets. He called these packets quanta, and today we call them photons. Each photon carries a very specific amount of energy, and it's all based on its frequency. And here's the most important part. The interaction is always one-on-one. One photon hits one electron and gives it all of its energy. Einstein summed up his entire idea in this one beautiful equation. The kinetic energy of the escaping electron is just the energy of the photon that hit it, minus that escape cost, the work function. Let's do a quick example. Imagine the escape cost for a metal is, say, 2 units of energy. If a photon comes in with 5 units of energy, it pays the 2-unit fee and the electron zips away with the leftover 3 units of energy. But what if a photon only has 1.5 units of energy? Well, that's not enough to pay the fee, so nothing happens. And that's your threshold frequency. And just like that, everything clicked. It all made perfect sense. If you make the light brighter, you're not sending more powerful photons, you're just sending more of them. That's why you get more electrons, a bigger current, but they aren't any faster. And the whole threshold frequency thing? Well, that's just the point where a photon has just enough energy to pay that escape fee. Einstein's idea of the photon solved every single piece of the puzzle. So, just when the world was finally starting to wrap its head around this wild idea that a wave, light, could also be a particle, another young physicist came along and decided to push things even further. In 1924, a guy named Louis de Broglie had this really bold and honestly beautiful thought. He was really into the idea of symmetry in nature. And he thought, hang on, if radiation, which we all thought was a wave, can act like a particle, well, shouldn't it work the other way around? Shouldn't a particle of matter be able to act like a wave? It was a radical idea based on this profound sense of cosmic symmetry. And this wasn't just some abstract philosophical idea. This hypothesis led directly to one of the most fundamental and mind-bending concepts in all of quantum mechanics, the matter wave. De Broglie came up with this equation right here. It says that the wavelength of any object is equal to a special number called Planck's constant divided by its momentum. And this means everything that moves has a wavelength. An electron, a car, you, a baseball being thrown. Now, you might be thinking, I've never seen a baseball ripple through the air like a wave. And you're right. That's because Planck's constant is an unbelievably ridiculously tiny number. For something big like a baseball, its wavelength is so small that it's completely impossible to detect. But for a tiny little subatomic particle like an electron, that wavelength is actually big enough to measure. So where does all this leave us? Is light a wave or a particle? Is an electron a particle or a wave? What's the real answer here? Let's just do a quick recap of the key formulas that got us here. You've got the work function and photon energy, which came out of Einstein's brilliant explanation of the photoelectric effect. And then you have the de Broglie wavelength, which is what gives matter its wavy properties. These equations are basically the instruction manual for this strange new quantum reality. The final answer is, it's both. And at the same time, it's neither. The universe, at its most fundamental level, has this dual nature. Things we've always thought of as waves, like light, act like particles when they start interacting with stuff. And things we've always thought of as solid particles, like electrons, act like waves when they're just moving around. It all depends on what kind of experiment you do. That's what determines which personality you get to see. The thing is, the quantum world doesn't play by our normal, everyday rules. An object doesn't have to pick a side. It doesn't have to be either a wave or a particle. It can be both at the same time, existing in this weird cloud of possibilities until we actually look at it. This wave-particle duality, it's not a mistake or a contradiction. It's a deeper truth about the very fabric of existence. And it leaves you to wonder, what is reality anyway?